Bradford, take it away.
All right, let's rock. So how many people here have heard of Hadoop? Sweet. How many people here have downloaded it and tried to use it?
Yeah, that's the same exercise that I had. Yeah.
Fresh meat. So I'm Bradford. I'm one of the founders of Drawn to Scale, and we make a easy-to-use distributed database. So it can do most of what your traditional relational database does, but without any scalability problems. We speak native JSON and are built from the ground up to be distributed. So much less work to implement our system than you would with, say, something like Hibernate. And you don't have to worry about how much data you have. And we're built on Google's big table type model using HBase as a storage layer. So you really don't have to worry about scalability or performance. You can slice and dice your data, filter it, group it, do everything else in a matter of milliseconds, no matter how many data, how many users you have. Just a little bit about me. I've done many odd things. I do some Hadoop consulting if you guys have big data problems that you want to solve. I've got a CS degree, and as well as a political science degree, and spent some time doing campaign management, some time playing metal guitar, a little bit of time in finance, and about a bazillion other things. But Hadoop has been my true passion for the past 2 years. Yeah, next year, I don't know, it'll probably be Clojure again or something weird like that. Which, if you haven't checked out, Clojure is way cool. So we're going to I want to talk a little bit about what Hadoop is, how it's being used today, and then give some concrete examples of the Hadoop ecosystem, things like HBase, and then go through an example of how cascading, which is a really great library to use Hadoop, is implemented. And we're going to use my amazing artistic skills here, the first part, to understand why Hadoop is important. So you can think about not too long ago, back in 2004, sort of the scale that we had data at. If you're a company like Amazon, it was pretty simple. You had a person who wanted to make a transaction, and they would give their monies to Amazon, and they would record that in their database. A few kilobytes of information transaction, maybe a few hundred gigabytes or a terabyte or two of catalog information. And that's really it. I mean, that was the entire ecosystem. But if you think about the data ecosystem behind a transaction, 2 years from now and now, it's going to be really crazy. Somebody probably talks to their friends online about, what cool laptop cover they want to buy. They might Google for it. They'll check opinion if that's still around. I don't think it is. I could be wrong. They'll check Amazon recommendations. Then they'll go buy it, and that'll be recorded in a database somewhere. Meanwhile, they'll probably tweet about it, or they'll go onto my Facebook, just say, hey, I love this thing. My laptop cover has drastically changed the quality of my life. Maybe they'll blog about it and check in at Laptop Land on Foursquare. And because of APIs and all that stuff, anybody can collect all this information. And so if you're an Amazon dude here with the cool glasses, you can integrate, probably dozens of kilobytes to megabytes of information just from one person's transaction or one person's purchase. And so, data is growing much, much faster than the ability of the classic database to manage it today. And all this data is interconnected too. Think back to 2004, you had your recommendations database, you had your retail database, purchases. And so, every time somebody clicked on something that was recommended, it would end up in a web log somewhere, server log. It would end up in a purchase database. Not that much data. But today, as I mentioned, everything is connected to everything else. Your tweets are about the products, and that can correlate to the database. And then they can track your movements on Amazon's web logs to see what time you were there. They can trend what items are purchased by what hour based on correlation between their database and everything else. So and this kind of becomes an exponential problem because every piece of data can be connected to everything else. And we're seeing this big data not just in social media, but everything from aerospace. I think the average 787 produces like a terabyte of data an hour or every few hours, to even power meters. one of our potential customers streams data from millions of power meters across the Albuquerque area. And so data is everywhere, and it's really exploding because it's all interconnected. So there's this new kind of business out there, or it's a new kind of business model. I call it data-centric business. And it's kind of novel because it didn't exist a few years ago. But they turn data directly into money. Whether you're an analytics company like Omniture, or you're somebody like Flightcast, or a little three-person startup who predicts if your flights are going to be late. All they do is turn ones and zeros into money. And it's a great racket if you can figure it out. But the problem is the more data you collect, the exponentially more expensive your database and your database team costs you. Who here uses a relational database fairly often? Who has more than 100 gigabytes in their database? Who has more than 5 terabytes in their database? How big is your database?
29 terabytes, and it grows by about half a terabyte.
Cool. What kind of DB is it?
Oracle.
Weird. So, what's happening is, and the more data you get, the exponentially more expensive everything becomes. You start out with like 10 gigs of data and one dude and a MySQL box. Then you multiply that a few times and you've got 2 dudes and a $50,000 box. And pretty soon you've got a team of 5 people who manage your database and a $250,000 box. Pretty soon everything's collapsing and you have to hand over millions of dollars to Oracle. Or you have to build your own magic distributed database in-house. A lot of folks. Has anybody here ever had to shard MySQL or tried to shard MySQL? How did that work out?
It was so good.
Oh, that's good. One of my past jobs, we tried to maintain a cluster of 20 MySQL machines because we had a massive amount of concurrent writes and reads, and we can never get the thing in a consistent state. And if something fell over, we'd have to manually restore it, even though it said it was automatic. And when you make a classic database distributed, you lose a lot of functionality. Like joins become very hard because joins are very CPU and memory intensive. And you can't do a join across a network because you don't have nearly as much bandwidth. So, you want to double your income by doubling the amount of cool stuff you can do with data, but pretty soon the cost of that is 10 times as much. It gets to the point where even with a few dozen or 100 terabytes of data, or I've seen companies with just 40 gigs of data, you hit a stopping point and your business can't grow, or you have to change business models simply because you have too much data. And you have to become distributed computing experts to get the thing to work. And that really sucks. So what Hadoop does is it's a batch processing framework and distributed file system for handling really large amounts of data. It's modeled after Google's Google's Google File System and MapReduce, and it provides both a framework for distributed computation as well as a way of distributed storage. And so you can think of it in this really technical diagram as work is distributed to hundreds of nodes, and by conforming to a really simple API based on sort of a Lispy functional map and reduce phase, you can get your distributed results. And the cool thing about the results is they're all stored in a file system, so even though you may have a 64 gigabyte file scattered across 100 machines, it'll just look like one file to the user. So you can download it, explore it, cat it, grep it, do whatever you want. So Hadoop is used hundreds to thousands of companies now, from really large to really small installations. Baidu, which is a huge search engine, I think in China, they have clusters everywhere from 10 to 500 nodes, and they store 3 petabytes of data a week in it. Facebook does a lot of log processing, analytics, and machine learning on about 1,500 nodes. It's probably doubled since the last time I made this. They probably have 15 to 30 petabytes of storage. They also use HBase to power their internal mail application. Hulu, everybody's favorite way to kill a few hours every day. We use HBase to store metadata about their videos, and they have log storage as well on 13 nodes. The New York Times uses it for bad language conversion, and StumbleUpon has 40 HBase nodes that power some of their Stumble engine, as well as the super link shortener. So, Hadoop architecture, there's two major components. There's the name node that stores the locations of all the files and metadata associated with it, along with the data nodes. So a 64 gigabyte file may be broken up into a few million or a few thousand 128 megabyte blocks. Hadoop is all about scanning through large amounts of data really quickly. It's not a database, it's a batch processing system and file system. So each of these blocks is replicated across racks and across nodes, so that at any time you can go pull a few nodes, or a few nodes can die, and you won't even know. Everything will fail over and balance instantly. And you can even tell what racks, what nodes are on, so if you lose an entire rack or if a switch goes bad, you won't lose any data. And the clients read directly from the data nodes. There's not really a bottleneck in the main node itself. So if you want really high concurrency access, with millions of users or hundreds of thousands of users, you don't find a bottleneck in the main node.
Bradford, quick question right here.
What's up?
There's only one name node. I mean, I understand the data being replicated across systems. Is the name node itself fault tolerant?
The name node, you can use standard HA tactics on a name node, RAID, replication, stuff like that. It is a small single point of failure, but Yahoo has several dozen really large clusters, and the past, I guess, 4 years of running Hadoop, they've had 3 or 4 complete failures, and 3 of those failures were due to doing an upgrade wrong, and 1 of them was due to a crashed name node. So statistically, you're probably not going to lose it, just like statistically, you're probably not going to lose your main database. But that being said, Facebook has written something called Avatar to basically replicate the name node and provide real-time backups that way. That's similar to what Google does.
So, question before you leave the HDFS. So we've been hearing a lot about the cap theory stuff, right? You have to trade off one versus another, right? So which one do you trade, right? Which one is weak on, right? Consistency, availability.
So, cap theorem is kind of odd because it tends to apply to single parts of an architecture as a whole. HDFS is very consistent and highly available and has a slight delay on partition tolerance. So in other words, your data is there to be read and you know it's the latest version when you're reading it. But if a node goes down and it hasn't replicated yet, you may lose that data. The replication stream is usually done in the order of milliseconds. So at most, if something goes down as you're writing, you might lose 1 to 2 blocks.
If you're doing the partitioning, isn't that normally the assumption you lose an entire data center, right? I mean, if you're a serious company, don't you assume you have to replicate between data centers?
Right.
To get true network partition survival, so you lose the entire data center because something back overs,
Right.
And so it's like, you can't be replicating that in milliseconds, right? I mean, that's good.
There-
Usually it's going to take seconds to go across the country, speed of light, right? So it's not
Right.
fast, right?
Yeah, if you do, so there's a way to say what machines are in what data center. And, with multi-data center replication, if, there can be massive latency there. So if you lose something, if you lose your entire data center as you're transmitting that block, then you'll lose the block. The upside of that is, since you don't have to check, you don't have to do like quorum reads on blocks, you get much higher performance in a system that's kind of like Amazon's Dynamo, where if you want to be sure the data you're reading is the most up to date, you have to read 3 or 4 replicas and then compare the timestamps. So there's trade-offs to everything, but in practice, I found this model to be a lot simpler and easier to use. But yeah, it's a really good point too. Any other questions before we go on? Cool. So here's a pictorial example of how the MapReduce algorithm works, and then we'll go into a word count. So the mapper, you've got this file spread across all these blocks in your file system, and the mapper reads it basically as one giant file. And so if you've got 2 nodes here, it will say, on the first node it may say, okay, we've got 2 hexagons, 2 blocks, and on the other node we've got 1 hexagon. And so the mapper on one node will sort of perform all the aggregation and all the operations you need. And then on the reduce, and then it will sort everything. So it'll say, all right, I want all hexagons to go to one node. I want all triangles to go to one node. And then it'll aggregate them there, so you get the final true total count of, I've got 3 of these, 1 of these, and so on. It's pretty simple once you get into actually writing the code, but here's another example. So if I've got a 3-line text file, each of these lines may be stored on a separate server. And so what you do in the map phase is you count how many times each word appears on each server, each little block. And then you do the shuffle phase, where it moves all keys of the same type to the same machine. So all the bears end up on one machine, all the cars end up on one machine, all the deers, and so on. And then the reduce phase basically turns key 1, value 1, key 1, value 2, key 1, value 3 into key 1, comma, value, the sum of values 1, 2, 3. So you can see that at each stage the data is sort of replicated but also reduced at the point, well, diminished in size. So that when you get to the final result, so each of these is viewed as a separate block in one file. And then your final result file here has the complete count of everything. Questions on how MapReduce works?
This is something that I've always found difficult to understand sort of intuitively about this process. The piece in the middle there. Mm-hmm. Don't I get tremendous, since it seems like at this point every machine wants to talk to every other machine. Mm-hmm. Don't I get crazy package storms, network congestion, routing issues, stuff of that sort? It seems to me as if this is sort of, all of a sudden we all of a sudden have to face the music.
Surprisingly enough, no. But it can be pretty I/O-intensive. What happens is each machine runs a consistent algorithm to determine where the keys should go. So if there's 100 machines and each machine knows that bear will end up on machine 12. So the only communication you have to do is to move the actual results around. And in this case too, not in this example, but most of the time, if your raw input is hundreds of gigabytes of an Apache log, in the map phase you've filtered out sort of all the crud you really don't want, and you have the data you just need. So that 100 gigabytes may just be 10 gigabytes across the network. I/O is definitely a killer though.
But this is bandwidth. I'm not talking bandwidth.
Right.
I'm talking, and I'm not a network engineer, but I'm talking about routing issues. I mean, it all goes through probably one switch. Is that switch not going to be overloaded? I'm not talking bandwidth. I mean, we can have whatever fiber stuff. That's not the issue. But the latency of establishing all these individual connections and then changing and breaking them down, isn't that killing us?
Not really.
I mean,
there's
okay,
usually a lot
why
of
not?
switches.
Is this just in practice not? Or
is it proven that this will not happen?
Well, it's pretty much proven because I've run nodes of 40 or 50 machines. Amazon has nodes of thousands of machines. When it comes to switches, usually it's more like one switch per rack is your typical layout. And the algorithm is sort of smart enough to really minimize the amount of sort of port changes and switches that need to go on. I'm not much of a network engineer either, but I've found that the real killer isn't in the network, it's in disk I/O. So the more disks you have, the better, because usually this is disk I/O and network bandwidth are the real killers here, because you're reading so much data off disk and writing so much data to disk. Other questions?
So I know this is a simple example, and so probably this question's out of order, but is the goal of this aggregate results, or can you reconstruct the original input from your final results?
The goal of this is aggregate results. You usually can't reconstruct the original.
Yeah,
input.
because this looks very destructive.
Yeah, very destructive. Yeah. MapReduce is all about taking big, massive chunks of internal data and then sort of doing a processing on it and really focusing on the output of that process.
So this is for like statistical analysis,
Right.
aggregate results, this kind of. Okay.
So I'll show an example later about HBase, which is a clone of Google's Big Table, is all about sort of a standard column-oriented database where you store and retrieve data by rows and columns and all that. And you can use it as an input to MapReduce jobs, but it's a lot more sort of get data, retrieve data.
Mm-hmm.
Yeah, you mentioned I/O is the main issue. So would that be true even for a simple example like this one?
Well, really depends on how much data you have and how many disks you have. Like, if you've got 10 terabytes of data on 5 machines, you're going to be spending a long time reading and writing from those disks. But 10 terabytes of data across 100 machines goes extremely quickly. You'll spend more, for most algorithms I've seen, you'll spend more time waiting for data to be read from disk and written to disk than you will actually doing computations with the CPU. That's not true with every kind of workload, but for a lot of these sort of big data jobs, that's what I see.
This is partially, jumping ahead a little bit, this is partially a reflection of the fact that all the time everything is read, right? Because we don't have indexing.
Correct.
So, I mean, basically, we every single time we do something, we do a full table scan, except that we do it on 100 machines in parallel.
Correct. Now, HBase has indexing by primary keys, and our system, our database, has what you consider traditional secondary indices. But Hadoop itself is not meant for random access of data. It's meant for bulk processing. HBase partially solves that problem by letting you partition things by key range and stuff like that to read only, if I want to get row number 008, I get that instantly. Other questions? All right, cool. Good questions so far. So there's all kinds of workflow tools that will help save you from writing traditional MapReduce code, and I'll go into more of those later. But sort of as an overview of the system, there's Pig, or overview of the ecosystem. There's Pig, which is sort of an ad hoc workflow language. You can think of it as the query planner part of something like SQL. Then there's Hive, which is a SQL-based data warehousing tool. And my favorite, the one that I use a lot, is Cascading, and it's very lightweight, very powerful data workflow language. And the thing I like about Cascading is that it's all in Java, and instead of being a scripting language, so I don't have to use my tools the way somebody else thought I should. I just write my code, make my Java objects, and sort it. These primitives you see on the bottom, group by, every, each, they work on tuples in the Cascade lingo. So I provide a way to really abstract away all the distributed computing MapReduce stuff into really simple to use primitives. Other things in the Hadoop ecosystem that are really cool is Zookeeper, which is sort of a way to do all the painful distributed stuff. So it's a distributed, very small file system, and it lets you keep track of nodes, does heartbeat analysis when a node dies. You can do leader elections, you can lock on resources. It's a really clever way of basically abstracting all the stuff you typically have to reinvent in distributed systems into one place. HBase uses Zookeeper for managing, so each of your HBase nodes is a file in the Zookeeper memory. And Zookeeper will ping your nodes, and if your master node dies, it'll bring up a new one automatically. And Zookeeper is seamlessly replicated as well and really highly consistent. So it itself is a fault-tolerant system. So I've talked a lot about HBase, and it's one of my favorite things out there. And it's a distributed, extremely fast column-oriented database that's modeled after Google's Bigtable. And much like how Bigtable runs on top of Google's file system, HBase runs on top of Hadoop's distributed file system. So it's real-time and random access. It's as fast, it's almost as fast per node on access as a traditional like B-tree indexed relational database. But since it runs over hundreds of nodes, you can do scans and gets extremely quickly with really high concurrency.
So does this use the MapReduce underneath also, or that's what it?
So you can do MapReduce on top of HBase. A lot of people do it. But you can also just like use a REST interface or use a Java interface to get data and retrieve it by the primary key.
No, I mean like does HBase itself that uses MapReduce to get these columns out? It ignores all of that basically.
Yeah, HBase does not have its own implementation of MapReduce. It's really meant for storage and retrieval. We've actually been working on sort of a real-time MapReduce on top of HBase to let you distribute computations in milliseconds instead of minutes like you wouldn't do. But it's experimental, so but we're still working on it. But HBase is not really meant for processing. It's meant for random access and region or table scans. So HBase is used all over the place. Its heritage is Google uses Bigtable for almost everything, from storing your email to storing images in Google Maps. Facebook uses HBase to power, they're testing, I'm not sure if they're testing or in production yet, to power their mail application. Twitter actually backs up MySQL with HBase and then does analytics and powers their people search with it as well. There's been sort of interesting things happen in the distributed database space lately, where Twitter and Facebook both had to drop another database called Cassandra because it had severe reliability issues, and they've moved to HBase. And you may have noticed Dig had a lot of uptime problems with their Cassandra cluster as well. The thing I like about HBase is that it's extremely simple, and you get a lot out of that simplicity, but it's not that sexy.
Are you saying Facebook has abandoned Cassandra?
Yeah, they have, I think they might have one committer on staff to do some internal legacy stuff, but for the most part, they are switching their mail over to HBase. And I think they do a lot of, they have an HBase committer on staff as well, and I think they do a lot of internal analytics with it as well.
I mean, because they invented Cassandra.
Yeah, they invented it and then kind of left it alone for a year, and other people picked it up, but Facebook's never contributed to Cassandra, which is why it needed so much work beyond like getting their first version out. Anybody else?
It was just employed to sabotage other startups.
Probably. You're very good at evil. How long have you worked at Microsoft? So I know note, I worked on SQL Server for a year at Microsoft. Now that was an interesting code base. Anybody else? All right. So PowerSet, who's now Bing, had over 100 nodes to do all their indexing and serving their data. And StumbleUpon, uses quite a few nodes as well. And even Little Ning, has a small cluster as well. So I talked a little bit about what happens when you try to scale a relational database, and it really varies. Some people can have a 26 terabyte database and not have scaling issues. Other people, one of our customers, has like 100 gigabytes, and their queries are taking 5 or 6 minutes.
Did I say we didn't have scaling issues? I don't recall.
Okay. Oh, good. So, there comes a certain, as you saw earlier, with a traditional relational database, you scale up to a $50,000 box, a $200,000 box, a $600,000 box pretty quickly. And you get really diminishing returns. And there's a lot of reasons for this. Indexing doesn't scale quite linearly. Disk I/O doesn't scale nearly as quickly as the amount of users. Joins are very resource intensive. So there's a myriad of reasons, and if you try to make a relational database distributed, you start losing all advantages of SQL. You don't get joins. If you try to do top X queries, I want the top 100 authors per all my blogs. That's a very hard thing to make distributed as well. And pretty soon you just end up with like a key value store with a nice user interface. That really sucks. So a lot of times you have to disable secondary indices, which is one of the best things about traditional relational database. You have to handwrite your own access code. So if you've got 20 machines and you shard everything up by primary key, a lot of times you have to hash that primary key to get the different boxes. It just really becomes painful. So at StumbleUpon, HBase sort of actually enabled a new kind of business because they couldn't even conceive of how to do it with a distributed MySQL kind of setup. So StumbleUpon, how many people here know what StumbleUpon is? So StumbleUpon basically lets you stumble upon new web pages. You go to their site, you click thumbs up if you like the page, click thumbs down if you don't, and it'll take you to new pages. So a common thing I hear a lot when you get to too much data in your database is, we knew what we wanted to do, but the database just wouldn't listen. I've done a lot of SQL query tuning in my time, and it's like a magical black box to me. I have no idea, like if I want to select A, comma B versus select B, comma A, or filter A and then B, just like changing the order of things in SQL drastically affects what the query planner does, and it's never intuitive. And I've seen 100 or 200 line long SQL queries because people try to do everything on the server, really minimize their data, and then transmit it to somewhere else. And that's kind of a really common theme in Hadoop, is bring your workload to the data, don't bring your data to the workload. Because bringing your workload to the data may mean distributing a 100 kilobyte jar to 50 machines, instead of reading 50 gigabytes from every machine, getting all the data one spot, and then crunching through it. So on 24 nodes, with I think like 16 gigs of RAM and 4 SATA drives, I think each of these nodes costs $2,500. With HBase, they're able to write 1.1 million rows a second, which is pretty good for a cluster that maybe costs, well, just in hardware, something like $100,000, $150,000. So the HBase architecture is pretty interesting. Remember I talked about, so you've got Zookeeper clusters that kind of maintain the state of everything. You've got a master, which is replicated, so it's not a single point of failure. And you've got these things called region servers that run right on top of the Hadoop data nodes. And the region server, each region is a block, like a 64 megabyte block in your file system. And a region contains a sorted contiguous amount of keys. So if you have your hexadecimal keys, your first region may have keys 00 through 0A, and keys 4, 5 through 4F. And it's stored with an LRM tree, which basically lets you scan through in this 64 megabyte, scan through, and it's like a O of n log n or O of log n access, so 1 or 2 disk reads at the most to get to a piece of data you need. And so, these blocks are replicated across the entire file system. So if I want to retrieve blog number 3800A, goes right to this block and retrieves it. And each client maintains a up-to-date, each client has a way to basically maintain seamlessly an up-to-date knowledge of where all these blocks are, or where all these regions are. And so you can read directly from the clients instead of having to go through some kind of master node to tell you what machines to read from. So, questions on the HBase architecture?
I somewhat did miss something. So, what's actually being stored? I mean, is this structured data? Is this anything? Is there some sort of data definition to what I'm storing?
Yeah, that's a good point actually. So HBase is schemaless. You can serialize things to it. We serialize JSON to everything. What's actually being stored, it's column oriented, so what's being stored on disk is 1 file per column. I'll actually show you here. So what's being stored on disk is 1 file per column. In that file is a list of keys, or 1 file per column family. In that file is a key value. So, here if we're collecting logs, key, this row key, and this author column family will be one complete file in the file system. So a column family contains things called columns, and you can just sort of think of it as a map, like in Java, where it's a map to maps. So, key 00A gives me column family, and I want to get to column family author, and inside that column family may be several different columns. The domain column, the page rank column, and there's no set schema to it. Everything is serialized down to bytes, so it's really flexible. And each of these columns is stored on in the Hadoop file system. Yes.
And how do I search it? I mean, do I have to search it by row ID, or can I search by find me everything with name equals bar?
So that's a really good point. Since there are no secondary indices, if you want to search by anything other than a primary key, you're basically doing a table scan. What Google does, what a lot of other people do, is they denormalize and duplicate. And so there's no joins in the HBase world. But since these run on very commodity boxes with SATA drives, if I want to access all documents by author, you would create a new table and then store, document ID by author that way. I've seen places with 30 or 40 columns stored in 30 or 40 tables, and it seems kind of inelegant, but since everything is storage is so cheap, it actually turns out to be all right. My company has written secondary indexing on top of this, so you do get the fast queries and scans and stuff like that.
So is this why it's so popular for like log analysis and stuff, things that are like write once data sets? Like there's no update column, right? Because you never log is never updated, right? So I can write it one time, so I can denormalize that if I want to do, and because I'm never going to go back and change what the data was. But it seems like if I denormalize it 30 times and then I change Bob's name or change something about it, don't I have to go and find all those 30 records and somehow update all 30?
Yeah, that's a good point. So it really depends. That's definitely a really common use case. A lot of times, what I found is that most data access patterns require updating just a few things at a time. So updating a bunch of denormalized tables can be a real chore, and it's something you have to do in the application layer. I've actually seen surprisingly few data sets that do that sort of denormalization, deduplication thing. But you know, for things like analytics, BI, and stuff like that, where you want to be able to slice and dice by a bunch of columns in real time, you don't want to do table scans. And that's sort of where our company stepped in and wrote distributed secondary indexes, just like you would have, you know, in MySQL. So I only have one table instead of 30 tables, and I have to maintain concurrency between all of them. But yeah, that's a definite need.
If you are going to update multiple things, is there a notion of doing that as a transactional thing where it's like either all the updates happen or you don't just get like 3 of them updated and 6 don't?
You can use, there is transactional stuff in HBase, and you can use Zookeeper as a transaction sort of state maintainer, so there's a way to roll back and do it. But some of it you still have to write by hand, it kind of sucks.
Adding on to that, with the updates, let's say now my data model has changed, and I need to change the relationships, you know, that I've actually persisted, not just adding some attributes or, you know, but actually change the relationships. I mean, how do you do that in this type of system? I mean, with a normal relationship database, you bring it down, you run some scripts, you know, you create, you know, you change it, but with something like this, how do you do that?
It's basically the same way. What I would do is, most of the time you don't have to bring the database down to add columns or change relationships. What I would do is actually write a MapReduce job to sort of do the transformation, and then run that across the cluster, and maybe block writes or just write it to a new table. And you know, since you're writing Java code, you can do whatever you want. So it actually turns out to be, I've had to do things where I've taken a 50 or 60 table Microsoft SQL server layout and turned it into one table without throwing away any data. And it was all with maybe a 200-line cascading script. Most of that was just reading CSV files. So that's what you would typically do. In general, with these kinds of systems, and something I think you have to deal with constantly with relational databases is there's kind of 2 ways people work with their data. You have high throughput, high latency, where I want to process a few terabytes of data, but I'll be okay with the answer in a few minutes or hours. And low throughput, low latency, like I want a list of all my emails right now, a few kilobytes, or a few megabytes of data at most. And if you design a system to be great at one, you have to design a whole other system to be great at another. You'll never be able to run them, well, on traditional Hadoop, you can never do a MapReduce job in seconds because it's meant to churn through a bunch of data, write intermediate results to disk, and be really fault tolerant. Just as with a traditional database, if you try to do a complex processing job over your entire data set, you're basically going to bring everything to a screaming halt.
One question. So I'm not sure if I understand what you have here. So author is one file for all IDs, or is it one file for that row ID?
So each column family here is one file, and column family contains, per row, can contain an infinite amount of columns, just like a key value map.
So all IDs are, authors for all IDs are involved.
Yes. One file on the distributed file system.
And one more question. So there is this, it seems like when you're, a lot of the questions are, you know, like looking at it as a database where you're storing data forever. But it seems to me what you really are doing here is more like if I need some processing of some data, I put it in this system, I run my processing, then I almost remove that data. So it's not a permanent storage like a database would be. Because, you know, like one thing would be what's the point of storing last year's log that I don't need? And if that machine crashes, this thing is going to duplicate my data, right? So it's almost like whatever you need is there, not permanent storage.
That's a good point, and it really depends. Like Facebook keeps all mail in their HBase cluster, so users can drill down and access. Now, because what's mail? It's a user ID and a mail item ID. Pretty simple pair there. So Facebook, it keeps all their data in the system. A lot of times, what I've seen is people will actually, sort of store their very high concurrency, thumbs up or thumbs down on Reddit or Dig or things like that in this system, and then periodically run MapReduce jobs to aggregate the data, and then dump those aggregates to a SQL box to do really complex analysis. One of my consulting clients is a social gaming company, and basically we used Hadoop to crunch their 1 or 2 terabyte log files down and say, by all male players, by all female players, by all game groups, give me a file set of all their actions, like a total count of unique users and so on. And then they dump that into SQL Server and do some OLAPs to say, I want number of unique users by date, where users equal male. So Hadoop is used for bulk processing. HBase is used for low latency reads and writes, and then you use MapReduce to kind of crunch through all the data and dump it to a SQL box, where you can do the really complex analysis.
So I assume the examples here are more towards textual data, but you can probably store binary data or whatever you want to, right?
Yeah, all of this, there's no schema, although you can do serialization. So yeah, it's all, at the API level, it's all bytes.
I think in the sort of, to your point, in the long-term storage versus temporary intermediate stuff, one problem that I see sort of, and maybe we're not there yet, but 5 or 6 years down the road we will be, it may be very hard to figure out what author meant, since there's no schema, as you say, so chances are it will morph, and the current application will have an awfully hard time reading the data that was written by the application from a couple of years ago. I wonder whether in some of your consulting gigs you have seen this problem already. I mean, this is one of the things that where a schema, because it's set so in concrete, it has disadvantages, but there is a certain integrity to what the data means very often, which
Right.
I can see here being a real challenge. It doesn't seem like a challenge, but all of a sudden, if you look at something that was written 6 years ago, what the heck did that mean?
That's a good point. Everything is sort of kicked up to the application level, which has its advantages and disadvantages. In a traditional SQL database, I mean, your semantics, like the relationships are encoded by your foreign keys and how your tables can join, and you can kind of I can look at a printout of a table schema and understand pretty well how an application actually works. In this kind of thing, there is no schema. Now, if you store everything in JSON, there's kind of a schema on a row level because, I know this is an integer and this is a string. But there's not really any relationships here between what's in a column family per row. So with great flexibility comes great responsibility, because now your application has to be aware of what all this stuff means throughout the entire history.
Is this something that's currently being talked about in the NoSQL world, or has this particular train wreck simply not happened yet?
It really depends.
I mean, in terms of, for instance, versioning, that would be something that I'm sure people will eventually have to add by hand version ID to each row to be able to parse it later on. But this is something that beckons for infrastructure. So I'm wondering, is somebody already thinking about that kind of thing?
I haven't, with sort of more classic like single node document databases that have schema, they're a lot more sort of tolerant of those kinds of problems because they enforce a stronger schema than this. These kinds of systems are usually used to solve problems where that just wasn't an overriding concern. But it is a really good point, and it'll be interesting to see, especially in the enterprise world, where you've got 1,000 people who need to access this, and you know, it may have changed over 5 or 6 years, and suddenly they don't know what their data means anymore. That's a bad thing. With our startup, you know, because we provide sort of a schema to this big table approach, it mitigates some of those concerns. But yeah, in the end, a lot of things kicked up to the application level. As far as versioning goes, one thing I forgot to mention is everything is actually natively versioned in HBase. So every change you make is time-stamped and stored, and you can tell it to store the last 3 or store the last 10 changes. So the API is really simple when it comes to accessing this. You tell it what row, you can do a put, like a put or update of a single row. Tell it what column family, what column, and what value you want to put there. You can do a get as well. You know, retrieve things. I want to retrieve all. Metadata for the author by row ID 12, and then you can do a table scan where you scan between a range of row and indicate what column families you want to pull. And really, this is, I mean, for storing and getting your data, this is handles quite a majority of the use cases. In our system, we provide sort of a serialization layer in between, so you do get the advantage of the schema. But for the most part, your API kind of looks like this. Any questions? What time is it? All right.
One more question, I guess. Is there any notion of access control as to who's allowed to get the row? Or is it just simply row ID and you can read it?
Yeah, there is, I think, Cloudera, there's standard Unix access control plus some custom stuff for Hadoop itself. And HBase, Cloudera, who's the big Hadoop and HBase support company, is rolling out a security and encryption model now that has kind of traditional ACLs, what users can access what tables or what rows, things like that.
Okay, it's basically the file system, the Unix file system is the code.
It's a little bit of both. But yeah, there's not much security like you would see in like Microsoft SQL Server.
Going back to your example, like what would a row ID look like? Is that just like an under, or is it it's the key? Okay.
Yeah, row ID can be whatever you want. You can be a automatically increment key, like incremented primary key, like you'd have in a traditional database, or it would be like a UUID or something custom. So I talked about most of these, but the main thing about HBase is that it's built from the ground up to be distributed, and it doesn't let you do things that don't work well in a distributed world, like joins, stuff like that. And we talked about CAP theorem. HBase is very highly consistent as well, just like Hadoop. So if you read your data, you know you're reading the most up-to-date version instead of having to basically find a quorum between 5 or 6 nodes and then do a Lamport clock or do a timestamp, which we all know timestamps are horribly unreliable, to figure out what the real version of your data is. And of course it runs on really cheap hardware. We do all of our testing on the Amazon cloud, even though the throughput is really horrific on EC2. As much as I love it, the disk I/O is not that great. We run it on like nodes with 4 cores and 8 gigs of RAM, and it runs just fine. So I want to walk through a code example using cascading of sort of a real MapReduce job. And it's not uncommon in the real world to have one job. One application may have a bunch of different jobs and steps. If you're processing log files, you may want to, do geographic region processing by IP. You may want to do, cookie identification, all kinds of things on top of your data. So, giving an example here with cascading, it's really hard to think in terms of MapReduce because MapReduce fundamentally works on keys and values, and you may have to chain together 14 or 15 different stages. And the word count example I showed you, in the map phase, you emit, horse, comma, 1, cat, comma, 1, horse, comma, 1. It's not really intuitive to think functionally that way, unless you're a Lisp hacker, and I am not that great at Lisp. So, the thing cascading does is it abstracts away everything into fields and tuples. So, instead of, key 1, value 1, you have, you can think of it kind of like a traditional database. Your field, author name, field, document text, so on. And each of those fields has a value in a tuple. And then instead of just writing Java code through maps and reduces, you have pieces of functionality. Like you have pipes, and each pipe can have a filter or a group by or a sum or a count operation inside of it. So this is an example of with just a few lines of code. Traditionally with raw MapReduce and Hadoop, you have to coordinate the inputs and outputs of all these processing steps. But with cascading, it's much more straightforward. So I talked about functions and filters and things like that.
An example of a code.
Yeah, we'll get to the code example in just a few slides.
Before we get away from the MapReduce, you said earlier that the goal is to take the operation to the data. It seems like with the descriptions of the MapReduce, it always seems like the data is the one that's doing the moving. Is that just...
It's a little bit of both. You push your operations to the data as much as possible, but it's nearly impossible. If I want to do something on a global view of my data, it's hard to avoid shuffling it around. But the goal is to reduce your data so much in the initial processing phase that you don't have to shuffle around your entire data set. So if I have a 64 gigabyte word list in the map phase, I may be able to get that 64 gigabytes down to 1 gigabyte of words and like a count of those words. And so you reduce the data set, you have to shuffle down quite a lot.
That reduced is that it is actually sent across the network to the guy who's aggregating that phase and then
Yeah.
again. Okay.
So yeah, each node in the reduce phase, each node aggregates a small piece of your data. So it's totally distributed from beginning to end, but there is that shuffle phase. Real world example on that multi-terabyte data set I did for the social gaming company. I'd say we spent about 80% of the time actually reading data from disk and doing the MapReduce operations, and maybe 10% of the time actually doing that shuffle phase. And that's all copying stuff over the network and then writing the disk again. So that's usually not your limitation. And the cool thing about the shuffle phase is that there's algorithms that kind of do it asynchronously. So as soon as you start processing your data, you can start shuffling it. So you can sort of, it's not like you do one step, stop, do another step, stop, do a third step, stop. It's a little bit of everything. So yeah, the good thing about things like cascading is that you write these fundamental things just like you have in SQL, groups and filters and so on, and you can chain those into new operations. Hey.
Question, is Hadoop something that you can just download to one machine and run a sample app on one machine, or do you need a distributed systems to run it?
No, I do all my development on like a single box. If you can actually download, if you go to Cloudera's site, cloudera.com, you can actually download the Cloudera desktop, and it's a VMware image, and you can just install it. It comes with the dev environment and everything else, and you'll be able to write all your test code and do everything on just one node. Amazon provides this really great thing called Elastic MapReduce, which is basically Hadoop as a service. You can upload a Hadoop jar, tell it how many nodes you want to run on, and it'll stream your data in from S3 or elsewhere and actually do all the processing and then shut down the cluster. So you don't have to buy a bunch of boxes and keep them up 24/7. So here is some code that basically does regex matching. This is raw MapReduce code that does regex matching on a text file. And so you've got, some sort of configuration stuff here. A mapper takes a key and value and outputs a key and value, and then uses a reporter to sort of update status and all that. And this code here is just sort of pipeline code to match a string against the regular expression. Just sort of standard stuff. And then you do you output to the collector itself to say, all right, I want to output the result of my regex match. So you can see here, so this is about half the code. In the mapper, for standard MapReduce, it's really not that bad. But imagine having to write this much code for every single piece of your data. And then there's, for every step for every MapReduce job, you also have to do a bunch of pipeline stuff, or just sort of, pipe work junk. Set input format, to say, this is a text file, my keys and values are all in text, and so on. And then do some more configuration, use this string to match against, and then finally kick it all off. So you see, but cascading makes it much simpler. All that functionality is reduced. I mean, this is about just a third of much code. You define a scheme here, let's say, so it's kind of like a SQL schema or reading in a CSV file. I'm looking at an input file, and each line is offset so many bytes from the beginning, and so on. Pretty simple. And then you create a source tab that basically says, from the file system, read in all these files from the file system. And then you break that into fields to say, so you read the file in, and you've now got just these lines of text that don't really mean anything. And so then you define the fields you want to output. You can think of this as an Apache server log. Output the IP address, output the time the event happened, and so on. Then you use this regex to actually map to split that text line into these fields. So this actually line doesn't exist in here, but cascade, so I'm just going to imagine. And then you create a parser object to actually do that parsing. And then you create a pipe to actually apply that operation. So you can see here the parser is that regex parser. So this means for each line of that text file, apply this parser to that line. And then you've basically got, you just say here, all right, output it to a file of this file name. And the data type is just some more lines of text. So that's really it. You notice you don't have to understand the distributed MapReduce algorithm. You've got a bunch of primitives that kind of remind you of what SQL looks like. Some filtering or some grouping and so on. And then down here you basically just have some configuration stuff to say, here's where my pipe starts and ends. Go ahead and kick off the job and just wait until it's complete. So any questions on how this kind of stuff works, or this code example?
So this would be a part of like pig, right?
Right.
And then pig wouldn't be like this, it would be more like a set of file you write that is applied or something.
Yeah, Pig is more like a scripting language that compiles into MapReduce jobs. Whereas this is Java code that compiles into MapReduce. And the cool thing about this is it's Java, so I can kind of do whatever I want.
You can have multiple jobs, right? This
Yeah.
figures out if this has real.
Exactly. So loading all the data in maybe one job, parsing it maybe another job, writing it maybe a third job, or perhaps you want to parse it and then group everything by IP address or group everything by date. So you would just add a group by statement, one line, instead of writing another mapper, writing another reducer, writing a custom output format, and then writing all the configuration code. I mean, this, in our production system, we replaced like 3,000 lines of custom MapReduce with like 100 lines of cascading. Massive improvement.
So third-party library or part of Hadoop?
This is a third-party library. It's open source. You can learn more about it at cascading.org.
Brad, question for you. So what exactly happens at runtime here? I mean, this gets compiled into a jar or something like that, and gets deployed on multiple boxes, or it runs on a box and then it does the MapReduce part of it on multiple boxes? What's actually happening at runtime over here?
It's a good question. So what happens is you compile it to a jar, and then you copy that jar to the Hadoop job tracker, which just sort of kicks off jobs and keeps track of the status. And you say Hadoop-jar or Hadoop jar name, and it copies the jar to all the nodes. It sort of handles everything from there. So it's a pretty simple process.
Presumably it has to be some sort of Uber jar, like with all of your dependencies and everything.
Yes, yes.
What about the XML? There must be some XML somewhere.
It's JSON. It's JSON.
Yeah. Actually, well, with this specifically, there's not really any configuration. It's all Java.
There's madness.
I mean, how do you tell what computers go to talk to who?
That's all part of the Hadoop framework itself. So it's smart enough to know what machines to copy what data to, what machines need to run what processes. This is the totality of all the code anybody needs to write, where to parse an Apache log file, what to do. You
How's the
literally
data?
would compile this to a jar and copy this jar of the dependencies to the Hadoop master node.
And how is the data partitioning happening on the log file itself?
So, yeah, it's a good question too. If I'm copying a 64 gigabyte file to the Hadoop file system, it basically just partitions and chunks it into 64 gigabyte blocks, based just on file size and nothing else. And then inside Hadoop, there's this thing called a file input format, and it sort of handles the boundary conditions of, oh, I've got this piece of data on this machine, and part of this line is on this machine, and part of this line is on this machine. How do I read it? That code tends to be really simple. So, but when you copy a file to Hadoop, it's literally like just treated as a giant binary blob, and it is split accordingly.
So is this Cascadia, the jar for this Cascadia, does that reside on every MapReduce node? Or is it just one machine that then generates like standard MapReduce that goes out to all?
It depends on, you can think of each node as its own complete little world. And so if I have like dependencies inside my cascading job, like a regex library or something else, those dependencies will be copied to each node. So
Okay, what about the Cascade, the actual library that you use to?
yeah, this will be copied to every node as well. Yes.
So it's not like a standard MapReduce that it generates, it's more like it's MapReduce thing that.
It's a little bit of both. It compiles down to MapReduce jobs, but it also copies some of the cascading internal dependencies to each box for performance enhancements, custom MapReduce and stuff. But if you look at, I don't have a snapshot, but if you look at the actual job tracker screen, you can see it just looks like a bunch of MapReduce tasks. Right. So, and I talked about, here's a few of the primitives that cascading provides. operations on each line. You can group things. You can do operations by group. So if I want to group by male or female users, and then do a sum of all of the times they clicked on a certain icon. That's a group by and every and a sum. You can filter things, you can do assertions, aggregations, buffers, almost anything, any primitive you think you can do with data, you can actually do with Cascade. And everything is kind of reusable as well. So when you write code, basically the only thing you have to write, as you saw in the example, is if I want to apply an operation to each line, or if I want to group stuff, you just have to write the circles here, and the dependencies between everything is figured out automatically by the sort of graph generator, kind of like a query planner in SQL, but usually a lot less black box. And that planner then turns everything from the primitives you provided into mappers and reducers and stuff like that. So that's all I've got. Feel free to ask any questions you want. Fun.
So it seems like Hadoop and all this stuff is really geared more towards processing really large amounts of data. So I/O intensive, but not necessarily compute intensive.
I've seen both. I mean, Hadoop is more geared towards large data sets that require lots of I/O. It's not really a general grid computing framework like you would do weather cell analysis, or things that require hours and hours of CPU time, or things that require really low level MPI, where each node needs to be able to communicate all its data to every other node. Again, like a weather map, you can imagine. What's happening in this cell directly affects what's happening in this cell, and so on. So for things like that, there's a lot of grid computing frameworks out there, but they usually require a lot more custom code than something I can do.
So beyond like processing log files, or processing more sort of BI style processing, I guess, is it used elsewhere also, where it's not necessarily doing back stuff or back end stuff, more real time kind of stuff, things like that, or?
Not really. There is Hadoop is very batch oriented. Google recently released Percolator, which is sort of an incremental real-time processing platform, and there's work to make Hadoop a lot more incremental instead of very batch operating oriented. But for the most part, it's batching.
If you were using HBase as like a data store, and you wanted to serve up, say, email messages on Facebook, how do you serve as a client of HBase?
I'm sorry, I didn't hear the last part.
How do you serve as a client of HBase? What does it take to be a client of an HBase cluster?
So that API I showed you a while ago, to be a client, all you have to know is basically a...
So yeah, I remember the 4 parameters to the get and put and
Yeah.
all that, but how do you get a handle on that? What is the...
So all you have to know is like you can basically set up multiple client servers to serve requests in HBase, and so all you have to know is the address of any HBase node and make a request to that node, and the node will figure out where your data actually is. So, and basically you just require the IP of that node, and the client can do everything else internally.
So I would choose a node to interact with, and if the data wasn't on that node, then that node would ask the other node, and it would get the data. But I would continue to work with, say, node A, even though the data might be on any of the other nodes.
Basically. Most people just use the master node, and then the master node federates it out, but you can actually connect to any node and it will know how to serve your request. It's kind of like it's a big cloud of data.
But it doesn't overload that one if everybody goes to the master, for instance.
It usually, The only time it communicates to, I misspoke, so the only time it communicates to that node is to get an update of what regions are in what nodes. The client is smart enough, like the
Okay.
actual user client
So it has
is
sort of a
enough
smart
to know.
client that it keeps
Yes.
track of what just the topology of the cluster is. Okay,
Right.
that's kind of what I was wondering. So then
Yeah.
it knows the hashing mechanism, and then it can go directly to the node
Correct.
that would have the data for a given key.
Mm-hmm.
Okay, so and then another question that I had earlier was, do you name these databases, or for lack of a better word, so that you would have more than one kind of set of these things? In other words, can you have collisions in your key space, or can you have like another level of, hey, this is my named HBase with this collection of data, and then have another named HBase on the same cluster of machines?
So it actually doesn't hash by key. It partitions everything by actual size of blocks. And that's one of the things I really like about this system. So, about the big table model. So, like each region may be keys 00 to 0A, and then you make a request, the client makes a request to the server that has that region to get the specific row they want. So you can never have a key collision, unless like your application layer or something has, you've written your application that way. Everything is distributed by file system blocks, not by a hashed key.
But I guess what I mean is, if my application has two different kind of domains that happen to use the same key, but for two entirely different purposes, can I keep two distinct what this?
Oh, you can have multiple databases or multiple tables.
That's really what I'm getting at. I just want to know the terminology. So you call it a database in the HBase.
Mhm.
So I would name a database, and then within that I would do these operations that we saw them
Yeah.
put together. So
I would name the database, and the database has tables.
okay.
If you want to clean up, you can just do like a drop database and the data's gone.
Yep. Usually you can enable a lost and found in case somebody does something horrific. But, you basically drop something in the file system and it'll just mark the blocks as unused. Then it'll overwrite them in time.
So you don't need to sort of manually go and write some code that sort of loops over all the entities in that data set that deletes them one by one.
No, you drop a table and it's basically gone.
So do you have any experience like working with an app producing like a more statistical programming type stuff?
I don't, but there's been a lot of movement for, I know a little bit of R, and there's been a lot of work with integrating R into Hadoop. I don't really know much beyond that, but it's definitely something that's becoming more common.
So one of the things file systems have to deal with is fragmentation, especially with all this intermediary data happening and all this stuff going on. Any idea as to like how does HBase deal with that? I mean, is it always smart about allocating chunks of memory?
Basically,
like that?
it always allocates chunks evenly, and as you add new servers, it will automatically rebalance the data over.
Is there much of a cost to that? Like I would have thought that would be potentially expensive.
Well, you do have to move everything over the network, but it's done sort of gradually, so it's smart enough to sort of tone down the movement of data if you're doing a very intensive process, and then when things aren't quite so busy, it'll allocate more bandwidth to feed stuff over.
You can just dynamically add and remove nodes.
Yes. We've got it to the point in our system where you plug in a box and you come back like an hour later, and the OS is installed, Hadoop is up and running, and data's already being copied over.
Are most of your clients hosting their own clusters?
Yeah, surprisingly enough, when it comes to doing sort of I/O intensive databases, the cloud, especially EC2, is really not cost effective, especially because you have to use so many machines to get decent throughput. So one of our clients saves something like $20,000 or $30,000 a month by buying and hosting their own hardware instead of using EC2. One day the cloud will be there and it'll be perfect and beautiful and everything. But for distributed databases, it's not really recommended.
So the example you just gave, when you plug in the machine and everything is, so what technology do you use for that? Is that for the Hadoop?
That's just part of Hadoop. Well, some of it is chef scripts for us, some of it is OS install scripts, but the actual data rebalancing is all Hadoop.
Do you see any other competitors that are doing interesting things?
There's interesting movement towards sort of in-database, distributed database MapReduce in the data warehouse world. So companies like Vertica or Astrodata, they provide some of the advantages of a database such as SQL, but also the ability to do MapReduce on multiple nodes. But there's some really big disadvantages to them as well. They usually don't support a lot of concurrent users because they're data warehouses, and they usually cost a lot, and you can't do things like joins because you're still partitioned kind of by network. That being said, there's definitely a place for sort of medium latency, medium throughput calculations like on these data warehouses. They tend to be, and because they have indexing, if you just want to do MapReduce on a small set of data, they can be pretty fast.
How robust have you found the actual Hadoop code itself, the Hadoop stack to be? How often do you find that that it actually fails at the software level because something behaves incorrectly? Because it sounds like a pretty complex system, right? There's a lot of people talking to a lot of stuff.
It used to be really awful, like up until Hadoop 0.18, which was, I guess, 0.08. It would just crash all the time or just give me strange errors. But ever since 0.20, it's been really rock solid. The code, H-based code, I actually think is a lot more elegant than the Hadoop code. The Hadoop code itself is kind of crufty. Usually, the core Hadoop is actually really small, and there's a bunch of sort of contrib things like additional file formats or planning tools or stuff like that. I ran a Hadoop and H-based cluster version 0.20 on about 40 machines that cost like $500 each. They're like 8 gig of RAM, 8 core, 2 generations ago. It stayed up for like a year, and I did really horrible things to it. But yeah, it used to be really bad. But Cloudera has done a lot of work to basically make it 24/7, 4 nines, 5 8 nines, I don't know, kind of thing. Anybody else?
Just one random question. What's for the distributed file system? What's the scale? I mean, is it 32-bit, 64-bit, 128-bit?
64-bit.
It's 64-bit.
Yeah. The only limitation is
True?
what?
True 64-bit or?
Everything is, well, you can run it on 32 or 64-bit VMs, and it's smart enough to know what you're doing. But everything is sort of native 64-bit I/O the whole way. The only limitation, so there's no limitation on file size. The only limitation is on number of files.
Yes.
And the number of files, you can only have as many files as metadata will fit in memory on the main node. I haven't ever seen a case where that's actually become a problem.
I can introduce you to one.
Well, tell me about the problem.
No, but I mean, where we have directory structures with tremendous huge amounts of file.
Yeah.
And we have 2 limiting factors, which is one, the number of files. We have, well, 3. The number of files allowed within a single directory structure, and the number of total files on the overall file system, and the total file name path max length.
What I've usually
So
seen,
those are all limiting factors for us.
yeah, what I've usually seen is when you have that much data and you can't combine the files into bigger files, you use HBase and store each file as a row in HBase. And I've seen times when people like store entire videos in rows in HBase. And it seems a bit inelegant, but it's all bytes in the end. So it's kind of a trade-off between functionality and semantics and stuff like that. But that is a hard limit.
How does the file system just access through the Java virtual machine like an app from the file system?
Yeah.
You may have some special APIs.
It's mostly PO6 compatible, and you can use Fuse to actually mount it. And of course, there's a whole rich API.
Say a little bit more about the consistency model. If it's not doing like quorum reads, like how does it achieve high consistency? Do you think a database is right there, or they do a lot of extra work to make sure they're consistent? So that's part of why they're so slow, right? Then writing out extra copies and all to try right to guarantee that you know what the state of data is. Is Hadoop doing that locally, or is it not doing that, or is it where's the consistency?
It's pretty bare bones. I mean, the file system, really think of it as a file system, and that, when it comes to consistency, it knows when you read it won't let you read a block that is sort of an inconsistent state. And as far as HBase goes,
How does it know that though? I guess if you're in the classic problem for database, right? Halfway through the write, the machine dies, right?
oh, that kind
Right.
of consistency.
Right. But they avoid that by writing it twice.
Atomicity.
Okay.
Yeah, so HBase has, it won't let you do partial writes in a row, so internally it does atomic locking
Okay.
on the row level.
So it's trying to track that, so it's guaranteeing that you either get the
Yeah.
row, you don't get the row.
And if you need another layer, you can do transactions.
Okay, so that's part of why it's high disk I/O, because it's doing a lot of this extra work. I mean, that's usually that gives you extra overhead, right? The disk layer, rather than you don't
You
make
can
that
actually, yeah, that's a good point. You can actually tune sort of how often you want it to write to disk versus write to memory. So by default, it sort of does like 100 or 200 atomic transactions in memory and then flushes on the disk. But if you want really high consistency at the cost of throughput, you can have it flush every single write to disk.
All right, any other questions? I guess, thank you, Bradford.